Oop, that's not what I wanted to hit.
All right, everybody, we're going to go ahead and get started now that we're recording. I thank you all for being here. It's wonderful, and thank you for waiting for us to figure out the technology. So we offer these What's for Lunch for several years. We've changed the title. Come on in. And hopefully it gives faculty and students and staff a chance to just see what everybody's doing. So we are going to,
You want me to sit?
you're going to have to sit over there because the camera is right here. I know, I always look at the screen, but the camera's actually on the computer.
All right.
Come on in.
Hey, how are you?
Okay, how are you?
I'm good.
So today we've got an interesting discussion. When you sent it to me, it was about what we as faculty kind of made me think of learn when we have you all doing undergraduate research. You know, we're usually so focused on what you're learning, but we learn an awful lot too. So at this point, I'm going to turn it over to Dr. Manning and let you tell us everything.
Tell some stories. So, all right, well, I'm going to talk a little about different projects I have with students. And I use the term unexpected outcomes because a lot of times, that's it. Okay. A lot of times things happen that you don't expect. Sometimes they're good, sometimes they're bad. So one of the things I just wanted to give is a little background on kind of a philosophy. So one of the things that I do in research that I avoid is just teaching someone a task, right? And what that means is someone has a small piece of equipment, they get 20 samples, I show them how to run it, they go in, they run it, and they're done, right? They have no idea what they just did. They just did what I told them to do, right? So that happens a lot in research. People get taught a task, they do their task, that's great, but and there's nothing wrong with that. I mean, lots of companies have lots of people that get trained to do things like that, but that's not research, right? So research is uncovering new knowledge. So really what we try to do is to explore, right, an area. So you have your project, but you also want to understand how it fits in with lots of other things. So one of the things we do a lot is have people read, and that's important. And that's just to build up your knowledge base, right? And so the more you know, the more you see where your stuff fits in, you see what other people are doing, the competition is, that type of thing. And I'm a big fan, everybody has to memorize some stuff, but if all you do is memorize, you're not really learning that much, right? And I always use the analogy that a lot of people can relate to is, there's a guy that baseball's his hobby. He loves it. He can tell you who won a 1956 World Series and who was the starting pitchers. So all this stuff memorized does not make him a good baseball player, right? And so there's a lot of things in life that are like that. You can learn a lot about it, and there's nothing wrong with that, right? It's a great hobby. But if you're going to be a scientist, you have to understand things. And I think that extends to all fields. And then the other thing, when you start doing, researching, you'll see some of the scenarios students have been in, right? You start to see how the world works, and that's kind of important, right? And it's not all roses and hugs and whatnot. There's some cynical people out there. There's some people that will go out of their way to make sure you get nothing done, et cetera, et cetera. So that's an important thing to come across.
Maybe I won't work with it.
Put it down. So let me tell you about with the first one. And this was during the pandemic. I was working with some students right before it started on tuberculosis. We do a lot of work with TB drugs, and we were working on how to inhale them because a lot of TB, the bacteria is in the lungs. Then COVID came, and so we pivoted really quick. And in a nutshell, we ended up developing a therapy. When we published it, it ended up being kind of the feature article in this European journal. And the students were involved in this, right? So the whole thing. Now I won't go through the technology too much. I'll tell you more about the process. And so we were in Bailey every day, right? We were supposed to be banned from Bailey. We weren't supposed to be near each other, but we were in Bailey every day. And so every day I always like this picture because every day I give them a different assignment to do, different lab work to do. And it was 4 of them, including a UGA student because he got banned from UGA. So he was working with us. And they did the experiments for the day or the write-ups, whatever we were doing. At night, we were spending time, on a computer going back and forth, looking at data in Excel and whatnot. So this was the first thing that came out was this article, right? And it had to deal with, it wasn't really antivirals, it was with COVID, but And so after this came out, we got contacted by a couple of people. So one of them was the Brazilian embassy in Washington, D.C. They had a far worse problem than we did. So any country that had big ghettos where people were packed together and they have a weak healthcare system had problems, right? You just didn't read about that in the New York Times too much. So they were a country that had a big one. And so their person in charge of their science and technology at the embassy outside Washington gave us a call. We ended up having a number of interactions with them, and we ended up publishing a paper in the Brazilian Medical Journal recommending how this could be implemented. And so that again was something that students co-authored the paper, and they were on the phone with the ambassador, not expected. There was a medical doctor in Mississippi who was using the medications that had been prescribed for COVID that just didn't work. He said it was like giving people sugar. And so he ended up trying what we had published, right? And he did it what they call off-label. They adapted it. And so there he had, some very good results, right? And it cured. There were people, and these are people that were in the, in intensive care. It wasn't just someone coming in off the street. They had built up a bunch of phlegm, and nothing was working. So there we had 83 patients and then 200 controls. It went head to head with a drug called Redemsivir that had just gotten preliminary FDA approval. They were rushing things through, so things happened really quick. And him, as well as lots of other doctors, put stuff online that they've tried this drug, it does nothing. They don't see any change whatsoever. So in a nutshell, we ended up filing an application, 300-page application with the FDA to try to get our method approved. We had a lot of interaction with NIH, talking to their people, that's National Institutes of Health. We were also in contact with WHO, and we filed a patent application. So we were going through this, the students were working with me. So the FDA, we had several levels of these 30 to 45-minute online talks with FDA. I don't know what you call them, analysts, the people that move it up to level. And they never said no to our medication. What they did say no to was that we weren't big enough to do it, right? Which, how big pharma works, that's a perfectly fair statement. We ended up filing a patent application, and we're starting to build up a little bit of momentum, and then it was all over. And then suddenly everyone's like, yeah, it's not such a big deal anymore, right? So that was after like year 2.5. So this is one of those things that, the students that went through this with me kind of got to see the whole process, and I learned a lot too, the whole process of trying to take a drug to market, and how sometimes being in big pharma is more important than how good your idea is, right? So there's kind of a cynical side to it. Another thing that happened during the pandemic, right? Everybody was home for a while and whatnot. And then, we were communicating with students. I had these students and I worked on a puzzle. It has 170 infectious diseases in it. And it's what we call an abbreviation puzzle, right? And so the idea is that when you do this, you don't have to have any prior knowledge. You learn about infectious diseases as you solve the puzzle, right? And so we went back and forth and back and forth. And this ChemEd, this is part of the American Chemical Society, right? So it's their webpage for chemical education. It's been on air since 2020, and this got downloaded over 4,000 times. But what this did, with this, we kind of came up with a new way of learning in a way that we weren't given puzzles. Like if you do a crossword puzzle, you have to have prior knowledge, right? It's really hard to do like a New York Times crossword puzzle unless you know a lot of stuff. And so this was designed to teach people about infectious diseases, not to assume that you knew all about the Brazilian swine fever, but you learn a little bit about as you completed this. Okay. So that led to a couple other things, because I've been using different types of games and classes, not really games, but we developed a card game that was published on the thing. It has 118 cards, and each one's about a different element. And this you play like a regular game, and you don't have to have any prior knowledge in chemistry, but as you play, you pick up these little tidbits, right? So we call it like Snapple facts. You have the bottle of Snapple, you open it, and people read the facts, and a lot of people buy Snapple just because that's kind of like their urge to see what the fact is. People like to have that little bit of knowledge, right? You give them too much, they get overwhelmed. And so this game, they ended up, publishing on their website also. And I did this with some students. And then the other thing that we started with was we have a Nobel laureate crossword puzzle. And these are big puzzles, right? They have, maybe 50 things in them. And just like our first one, they're designed not to test your knowledge, but to teach you as you go, okay? And so the idea is if I just did this and you had to know a whole bunch about Nobel laureates from 1901 to 1909, very few people would even try it. But if it's given as, here's some knowledge. Now let's see if you can solve the puzzle, as you learn as you do. Then it becomes a lot more successful. And so now we have the whole series. We have two more decades to go. It comes out about every 6 weeks. And then, and this gets posted on airline too. So where did this ended up? And most of these were co-authored by students here, right? So I have people that work with me one at a time. And so they end up co-authoring it with, so that's a little bit of a resume fodder for them. So this past weekend, actually 2 of the last 3 weekends, I had 2 groups of students up in Atlanta at what they call pitch contest. That's where you go in front of investors and you pitch your idea to see if they're interested in investing in it. And so we adapted this game because let's be real, if you sell a chemistry game, on Amazon, it's not going to be a whole bunch of takers, not unrealistic. But if you adapt this model to anything, you want to learn about plants, you want to learn about, the whole history of the Hawaiian Islands. If you have a format that you can adapt to learning anything else in a card game, then, that might be of some interest. So this is Catherine Holster. She was up there twice. So this is Saturday, a few days ago, pitching this card game to investors right here, right? And so it was up at Georgia State. They do it. It's a Southeast regional type thing, although they pull a lot from the Atlanta schools just because they're close. And it gave her a chance, and she's in my freshman chemistry class, right? So this wasn't like a third-year graduate student. And so she pitched this idea to them, right? And everything went well with that. So there's a lot of times you keep following the breadcrumbs, right? And some interesting things can happen. Okay, so I'll jump down to another thing. So this picture was way back in like 20 years ago, 25 years ago. So there were 4 students and I. We went from the Okefenokee Swamp, Swanee River, all the way down to the Gulf of Mexico. And we didn't go the whole thing in boat, but we put in like 7 or 8 places at the boat to go look for samples. What we were looking for was remnants of DDT. So if you don't know what DDT is, in the 50s and 60s, it was used to knock out rodents and to knock out bugs. And they just sprayed it like it was, raining on it, in the middle of a rainstorm. They sprayed it everywhere. The problem was it was a carcinogen and it impacted animals, right? And so there was this famous book by Rachel Carson, Silent Spring, that was published, right, that really attacked DDT and the fact that the government was looking the other way and everything that it did wrong in the 1960s. So it also stays in your sediment for a long, long time, like decades, right? It doesn't go away quick. And so we went down, and so the reason we went to the river muck was because all the farms emptied there, right, over the decades. And so we figured if we got some cores, we might be able to see it. Well, so we ended up finding small hints of it here and there, but along the way there were 2 other things that we found. One of them was this molecule called chinchondin, right? And chinchondin is found in the barks of different types of trees that are on the Swanee River. It's other places. That's just where we were looking. And has a very similar structure to quinine, right? So quinine's a big deal because of malaria, right? So before there was quinine, there was malaria, which killed lots of people, right? And so that we thought was pretty interesting, right? And we ended up doing a little research, and we found out. I gave a talk at the ag station up in Tifton, and there was this really old guy there. And I said, we found this molecule, the chinchondin. It looks just like quinine. It's just one methyl group different, pretty neat. And he ended up sending me this book from like 1947, and it was things that happened during the Civil War that were odd. And one of them was that the quinine couldn't make it in past the blockades to the deep south, but they still had a big problem with malaria. So what they did was they adapted what the Indians used to do. The Indians used to take the bark from some of these trees and they would boil them and drink them when they had to deal with malaria as well as some other illnesses. And so we ended up finding this when we published a small paper on it, right? Correlating Civil War folklore with a natural product, right? With that molecule. And so no one looked at it in the Swanee River. It was just one of those things. It was like a 2-paragraph blurb in a book, and that was the only place we could find it, but it was there. And so that was pretty neat, right? And then the other thing that we came across was, and this was down where it was brackish water and salt water, was where the Swanee hits the Gulf, was the fingerprint for this molecule called bryostatin. And I didn't know anything about it then. It just kept popping up, and I looked up its mass and, and molecules you might find in it, and it just kept popping up. Well, in a nutshell, this ends up being a drug that has potential for neurological diseases, Alzheimer's, MS. It's successfully used against cancer, HIV, right? And it comes out of the ocean. And so we end up interacting with this lab called Gulf Specimen Marine Lab, which is in Panacea, Florida. And ironically, Panacea means cure all. Um, so to go backwards, this guy named Jack Rudlow, he's still there. I talked to him last week when I was down at his dock. Jack Rudlow was friends with John Steinbeck way back in the 50s and the early 60s, right? So Rudlow was a young guy. Steinbeck was a really old guy at that point. But Steinbeck wrote books like Cannery Row and Sea Cortez about these marine collectors on the Gulf Coast, right? I'm sorry, on the Pacific Coast. And Rudlow was a young guy collecting marine samples also, just starting out, like he's 21 or 22, something like that. And he wrote to Steinbeck. And they ended up having all these letters that went back and forth, right? And so Steinbeck encouraged him to, keep doing the marine collecting like the guy in the Cannery Row did. And Rudlow, and so what Rudlow would do is someone would contact him, say from a national lab or from university, and say, hey, we need 10 starfish, this species, can you do that? He'd say yes, he'd go out and get 10 starfish, ship them off. Someone else would contact him, say, hey, we're doing some work with trying to understand electric rays. Can you get us an electric ray? He'd say, yes, I can go out and get it. And so it's all the odd things in the ocean that most people have no idea they're even there, never mind where to find them. But he was in the water all the time, so he knew where a lot of these things were. Well, when we started our bryostatin thing, I'll point out that bryostatin right now goes for about $30 million a gram, right? So, well, so it's a well-respected drug that has a lot of potential applications, but it's in very short supply. So Suzanne was a English and biology major at the time. This goes back, and some of you may even remember Brian Adler. But we were going through Jack Rudlow's, one of his he has these old sheds where he has his marine lab. These are kind of like old wooden things that look like, the bulldozer is going to push it over any day. And we were going through some files, and Suzanne came across all these original letters from John Steinbeck. There was like 25 of them to Jack Rudlow. And so she was telling me the English major in her came out. She says, oh, this is a great find. Steinbeck's really famous, blah, blah, blah. And, we should do something about this. And I was like, well, that's nice and all, but, let's go take a shower because we just got out of the water. But we ended up finding out that people outside of science really, Steinbeck was, I think, described as the most published or the most read author of his century, right? So big name. And so we ended up publishing a paper in this journal called Steinbeck Studies. I never would have thought I would publish something in English literature, but it was all about their relationship and how Steinbeck stimulated Rudlow. So Rudlow ended up in the late 1960s, getting a contract from the National Cancer Institute. They saw him on TV. This is when they had 3 channels. And he brought a whole bunch of fish with him, right? So like starfish and this and that. And this was before we got just inundated with colored magazines, TV, and the internet. And so he's showing off all these odd things that came out of the ocean on this national TV. It was the Tonight Show, I think. It was a big show that everybody recognized. The next day, the National Cancer Institute called him and said, we'd like you to go out and collect 300 marine species for us because we want to test them for cancer. And these were everything from sand dollars to sharks. Right. And so he ended up doing this collection. And out of that 300, and this took place over years. It wasn't like, no, let's do it tomorrow. We'll get it done tomorrow. And then he shipped them off to NCI. And this is where bryostatin was discovered. And it ended up, of all the things that he found, bryostatin had the highest efficacy against the leukemia cell line. And so Rudlow ended up being kind of ground zero for knowing a lot about bryostatin in the marine environment. So great thing for us. Okay, and I'll come back to this in a minute. Along the way, I'll point this out. And Carlton was there last night, so he can testify to this. So we started. I always like shells. I guess when you're raised in New York City, where it's dark and dirty and everything, that shells from Florida are kind of an exotic thing. And so what we ended up doing with some of the shells is we developed some games. So we had this game we call the shell game, and I've done this with I've had students go out to a place in town where they have Alzheimer's patients and dementia patients, and they play this game. And they've invited us back. We've been back there a number of times. And then we do artwork on it with kids. You want to keep a bunch of kids. This we did last night. We were at a middle school STEM night. And so how do you keep, and so parents come up to your table with their kids and they want you to keep them busy. So what we do is have them paint oyster shells and they get to keep them. The kids love doing this, right? Some kids will sit there for 20 minutes and paint, 3 or 4 shells. The shell game is a number game. What you don't see on the other side is there's numbers. And in a nutshell, that we use different types of shells that look different because you basically you roll dice and then you have to pick shells. And so you have to, it forces you to do some simple math, 2 plus 3 plus 1 type of thing. And it also forces you to kind of remember which shell has what number under it, right? So that's where the house that we went to, I shouldn't say house, the facility that had dementia patients, this is the kind of thing that stimulates their memorization. And I like playing it a lot too. So we got this odd thing out of it, right? Is the different games. And so let me fast forward you. So this is, just an example of biopsy. If Alzheimer's has no treatment, right? If you get a drug for it, they're treating one of the symptoms. Like if you have the shakes and you have Alzheimer's, they'll give you a drug for the tremors. It's not doing anything to your brain. But bryostatin has been shown to have impact on Alzheimer's, multiple sclerosis, traumatic brain injury, Fragile X, several neurological diseases. It's not that well understood yet. Okay, so in a nutshell, we came up with a unique way. Remember, I said bryostatin is very expensive, right? $30 million a gram. So that really limits it. So we came up with this method called pharmaceutical aquaculture to make it in the ocean. What we figured out was that when Jack Rudlow did that search, that 26 of the 30 creatures that had activity against leukemia had bryostatin, right? And then there was one thing called bugulin aretina, an obscure marine creature that had the most bryostatin in it. But there's a funny thing with bacteria. So all these things had bacteria, and it's actually a bacteria making it. But bacteria in the ocean don't grow in a lab. So we decided we had to farm the ocean. And so this, for example, is what we did was we came up with a composition. This took us years to develop to grow that bacteria in the ocean, right? And we have had papers come out that are called pharmaceutical aquaculture. Well, we got our bryostatin out of here, and it's a little bit different than the one that the other people are talking about. I'll show you that in a second. And NIH agreed to test our bryostatin against a variety of viruses. Now, the reason that it was viruses is because viruses are the root of all evil, right? So there's bacterial infection, different types of cancer, neurological diseases that start with viruses, okay? And so this right here, so this is some of the ones that they tested it against, like dengue, cowpox, the yellow fever, different types of viruses. Our bryostatin didn't work against any of them. Okay, it did work against the one that we were hoping it worked for, this one HHV6. And this right here, I'll just read it to you, just I copied it right from the web. The earliest study in our review to suggest a link between HAV6 and that's Alzheimer's disease is based on the discovery of significantly increased viral load in the brain specimens of 80 patients compared to non-dementia controls with HAV6. So that's the virus that they think is responsible for a lot of neurological diseases. So that's why this not working against all these, but working against this one was kind of really good for us. And so what makes ours a little bit different is that if you looked at bryostatin, it's one molecule. And what we did was we captured the bacteria's chemical defense systems, right? So bacteria can't punch you, they can't kick you, they can't bite you, right? The only thing they can defend themselves with is chemicals. It's just like nicotine in a tobacco plant, right? There's a chemical defense. And so we actually had about a dozen molecules in there, right? And this, I should say, I could ship out 100 milligrams of this tomorrow, right? So how we make it is much easier and cheaper than how the 4 more prestigious schools and the 4 more prestigious companies make it. We have kind of like a grunt approach where we farm the ocean. So this was one of these things that, we've been working at for a while, and, we've kind of hit fruition with it now. So, and we're back at, a couple of national labs right now having our drugs tested for different things. So, okay. So along the way, we were spending a lot of time in the ocean. We started doing oysters. and oyster restoration. So this is not about food, right, at all. So this is a very much an environmental project. So one oyster can filter 50 gallons of water a day. So if you have a big oyster bar with millions or tens of millions of oysters, you can imagine how much filtration takes place. They're what you call a keystone species. So there's all sorts of different types of fish, crabs, et cetera, that get their start on an oyster bar. And there's a real interest in it because they prevent shoreline erosion. Worldwide, 90% of the oyster bars are gone, right? They've been basically picked to death or polluted to death. There's Chesapeake Bay, which used to be a major oyster place. That is 99% gone. And now the Army Corps of Engineers considers that a importance for our nation that they're stepped in to help bring back oyster bars there. Okay, so what we've been doing, so if you go around and you spend a lot of time around the ocean, you'll see a lot of concrete in the water. And a lot of times they have no oysters growing on them, right? Or like, and these have been out for years, right? And then over here, right, you can see maybe they're barely growing on. And this is after being there for 5 years. So this is one of our small, you can see right here, small pieces right here. And this is after 9 months. And this is the exact same location. This is at, it's about 10 feet away. And so that tells us there's larvae in the water. They're just not settling on that. And so this we put out, right, and we got oysters growing. And so that's what we're doing now is we've developed these novel materials that are a green technology. And we have permits from the Army Corps of Engineers and from the state of Florida to do this work. Let's see what I put on the next page now. So I'll point out a couple things that we came across while we're doing this. So one of the things is Georgia used to be a top producer of oysters in the country, right? It has a very fertile shoreline for oysters. But what ended up knocking it back was child labor laws, right? So a lot of little kids that were hired or whatever they do with kids that are 9 or 10 years old, and they were shucking oysters, right? And so they had a lot of disfigurement, like they'd lose fingers, you know, their hands would get crippled because that's a rough thing to do, especially, you know, if you go back 100 years. And so when the child labor laws kicked in, the oyster industry in Georgia dropped quite a bit. Another thing was you may not be aware of was 3 years ago, the Supreme Court decided on an oyster-related item in Florida that involved the state of Georgia. So Georgia and Florida went to war legally. Florida was claiming that its oysters in Apalachicola Bay were all dying because the water that was coming from Georgia into Apalachicola Bay was polluted and not enough. Florida ended up losing because they couldn't prove their case. So I don't know how much money that would have been worth, but that went on for several years, right? And so we were growing oysters, right? Where Florida said you couldn't grow oysters, right? And so ours was, and then we had a permit to do that and all. We were just dealing with a low-level tech at the Florida, Division of Environmental Protection, but we had oysters growing there with our material. The real reality was the oystermen just picked all the oyster bars clean, right? Because that was how they made their living. And so oysters have kind of an interesting background. Along the way, we've done a lot of work with cancer drugs. And I'll point out that we have NCI, National Cancer Institute, gave it its own name. And they call it kind of an obscure group, but it's a group of copper-based drugs. And I'll explain to you why they're kind of unique compared to others. So this is sample data from National Cancer Institute. And on this axis, this is concentration, right? And so this goes from 10 to the -4 to 10 to the -9. So that's roughly, so that's 5 orders of magnitude, right? So that is 100,000-fold. 100% is how the cancer cells normally grow. 0% means they've stopped growing. And then -100% means that you've killed them all. So a typical response when you do a drug that works, right? If you went to look at most of the drugs, if not all the drugs on the market, that at the higher concentrations, it works okay, but that's also where you have these terrible side effects, right? A lot of cancer drugs are actually poisons. And as the concentration gets lower, right, the cancer cells start growing better, right? So it's just like if you have aspirin, if you take like a little tiny piece of an aspirin, it doesn't do anything for your headache, right? You take 2 Advils, whatever you're taking, I don't even know, ibuprofen, then it goes away, right? Same thing here, that as the dose gets lower, it stops working. So this is our drugs with the red dots, right? Red here. You can see as the concentration gets lower, the percent growth stays low. So we can give like a part per billion of our drug where you wouldn't even know there's a side effect, and it's still knocking out the cancers at a similar rate as it would at a much higher concentration. And there's a very complex reason that we think we have for that, but they're interested in it, NCI. And so this over here, like, is leukemia, right? You can see the lines go straight across, right? So this is all from our drugs that got tested by them. And I'll point out, you see down here, there's like 6 blocks. So these are all leukemia patients. Everybody's cancer is genetically slightly different. And so you can look it up and you may find that, for example, this might have been, say, a 56-year-old male that worked in a shipbuilding industry and was exposed to, X, Y, and Z. And then they had it, his cells were donated after he passed away. So all these are different patients. You see here with breast cancer, right, go straight across. So it's still knocking out the cancer, but it's doing it at a very low level. And so this is something that we extended. I'll talk about pox viruses and then about TB, but this effect right here is very unique. Okay, so that's why they've been taking samples from us for about over a dozen years now. Okay, so that's cancer. So my class last year, as a year and a half ago, I had a medicinal chemistry class, and I always do a project in there. And the project we were going to try to do related to smallpox, right? So I'll give you a little background on smallpox. So it's a viral infection that's easily transmitted. From 1870 to 1970, roughly, it killed between 3 and 500 million people, right? So an incredibly deadly viral infection. It was eradicated in the 1970s by vaccine. There were never any drugs that you could use to treat it, right? If you didn't have the vaccine and you got it, there was a 30 to 40% chance it was going to kill you. And if you survived, it had terrible side effects, right? Like you lose your vision. It had all these, these pock marks on you that were loaded with inert smallpox viruses. So in the 1990s, a drug called TPOXX, and it has a couple of medicinal names, right, was developed and tested against smallpox in test tubes and then in animals, but there were no people to test it on, right? So it's been FDA approved based on the fact that you can give it to people and it doesn't cause terrible side effects, and then it stops smallpox in animals, right? But that's all they could do. So in 2023, the MedChem class and we were going to work on this drug and see if we can make it work better, right? And that was and we're going to do a lot of modeling, right? Obviously, I didn't have any smallpox in the lab. I'll point out only 2 countries have the smallpox virus, the US and Russia. And it's very much considered a bioterrorism weapon now, right? So if you have this easily transmittable thing, and you really don't have to have the original stockpile for it, right? Because the genetic sequences to everything were published, how to make it or how to alter other viruses. And so this is the kind of thing a small country or a big country could do pretty easily. And then just think about someone going through like a subway in New York or Washington with a backpack on, with a container of the smallpox, and it's just sending out this little tiny mist as they walk around, thousands of people. It'd be very easy to spread, right? So you don't have to have aircraft carriers and fighter jets and whatnot to do something like that. So the government is still very concerned about this. So show you what we did, right? And so this right here is the drug, and the bigger this number here, the SI50 number, the more it works. So I'll show you down here, copper by itself, copper chloride, copper by itself did nothing, right? So under 10 is considered inactive. Copper sucrose by itself did nothing, right? And then some of the other fatty acids and whatnot that we used did nothing. So these things by themselves did nothing, okay? And that we kind of expected. But right here, we have copper TPOXX. That actually made it get a little bit lower, a little bit less effective by binding the copper to it. But if you go up here to the top, you have copper sucrose, which down here had no efficacy by itself, actually made it work twice as good, right? So roughly the efficacy improved by a factor of 2, okay? And what it also did was disguise, because you can have antiviral resistance, like they had AZT, the HIV drug, you can have antiviral resistance. So this also could disguise this from becoming, or prevent it from becoming resistant. But you see here, when this is all data done by NIH, right? So they accepted it for some preclinical trials. And this is just one of the pox viruses they tested it against, right? And you can see it worked. And then you can see the fatty acids, you know, when they're working with the copper sucrose work some too. But and we have a reason why this wasn't a random selection. There was a lot of chemistry behind why we picked copper and then why we picked copper sucrose and then why we bound to this particular molecule. So this was a class exercise that ended up being really good. We have a paper coming out on this. And then this is when NIH started testing some of our other antivirals, right? Because we basically worked for free compared to some of the big drug companies and whatnot. And we were getting really interesting results. And so that's kind of an unexpected result. And then just it's like 3 weeks ago, I guess, something like that. So Dr. Laverne contacted me with about a deadline that just popped up. It was like 2 or 3 days away and said, "Do you have any posters for the Capitol?" And I said, "Sure, I do." You know, and so these two students, Capri and Akshil, have been working with me for 2 and 3 years each. And so we went to work and we summarized all our data into a poster, and they ended up giving you know I guess we say a poster presentation at the state capitol. And that's right when session's in, all the politicians are there and they're fighting for money. And so their job was to kind of heighten how much money universities need to run, I guess something like that. So this man right here is Ben Watson. He came out and talked to him. And he's the chairman for the state's Health and Human Service Committee, and he's a medical doctor. And they said they spend, like 5 or 10 minutes with him talking, asking about their project. So it ended up being a really unique experience for them, right? Good for them, good for the school, I hope. And, for us, it was, just one of those things that came out nicely. Is that the last one? That was the last one. So that just kind of gives you an overview of some of the stuff we're working on. So if you guys have any questions or want to discuss anything, happy to deal with it.
Thank you for that. That's always fun. I get to know about these because of the undergraduate research symposium. So I was enjoying looking back on some of the ones that we've had. But what questions do you all have?
I guess mine is more of a comment. So you said that how you made the drugs for your tuberculosis as well as your Alzheimer's. Considering that you made it bioavailable and as well as just from the ocean, I'm wondering how that would be affected by things such as climate change, especially when it comes to the increasing intensity of hurricanes, as to how vulnerable that production process would be.
So that's a better question than you think, because we've been hit by climate change. So I didn't put it up here, but we do coral restoration. We have a permit from NOAA to do that, right? And so corals are in sharp decline, and they're like oysters. They're a keystone species. Lots of things grow on coral reefs. And when the coral goes away, lots of stuff dies. And so last year, I should say twice we got hit by hurricanes, got wiped out. So we go down there. We have in the Florida Keys, there's an island called Pigeon Key. It's a nonprofit. They let us put our coral stuff there. I don't usually have a hard time getting students to go with me there. So, but go figure that. But go to New Jersey, nobody wants to go. We saw that coming. So we got hit with 2 hurricanes, Irma and Ian, and they both wiped us out. We got to start over again. It also impacted everybody else down there. But the thing that I've noticed, because I've been diving down there, scuba diving down there for almost 40 years, we used to go down and you see blue water. And I have pictures of you look out on the horizon, you get this gorgeous blue water, whatnot. Now you get pictures and the water's green, right? And there's just so much human nutrient from the algae, that places that used to be flatbeds where there were tarpon and there were bonefish and, just gorgeous to look at. Now they're green and you see green mats on the bottom. So that's a very real thing. That's, and there are people that did a lot more photography than me that have pictures like that, just all over the place. And it's not like it's this area here, like this little corner of the Keys. It's like kind of everywhere. And so that ended up, when we were doing our coral restoration, I could have a picture of it, we were getting corals to grow. And then as time went on, like even in a short course of like 3 years, this last summer, they had the highest temperature ever measured in the Atlantic Ocean was measured in the Florida Keys, and it was over 100 degrees. It was like 101 degrees. And so and a lot of times you see science data and it went up 0.1 degrees, and no one's saying, why is that a big deal? This went up from like 25 years before that. The average temperature was 86 in the summer. And then this place, now it was an average of 101. So that's significant. And that means there's a lot of things dying. And there's other things like bacteria and algae that are probably thriving in that nasty broth. So it does hit us with that type of thing. Our biostat work, we do on a panhandle, and that's far less developed than the Keys. So, but we have been hit with hurricanes there. So a lot of times that just means you get to start all over again. You have things that have been out there 3 years, and it took you 6 months to get it done. Hurricane blows through, and you're just starting over. So, but it definitely has a real impact. So. And you can Google that. That was like in the Miami Herald. That wasn't just like in some obscure science journal. They were publishing that everywhere. And the Florida Keys was panicking because it was negative about things going on there. So
Is this something you're gonna work on as well to fix this? Cause
that's
I enjoy your presentations and yet I become frightened.
well. So there's other ones like we've been going down there. I camp when I go down there most of the time, right? Because that's just much cheaper than staying in a hotel. Plus, if I'm good students, they spend a lot more time outside rather than sitting on a bed watching TV. You can see there's lots of newspaper articles on this, not just in journals. It's seaweed, right? And you see these things coming out of the Amazon River, right? And they'll be like 600 miles long and 50 miles wide of seaweed mats now. And then they'll come up and they'll hit the Keys, and you'll go to beaches that in the summer we used to camp on that now have literally 3 feet of seaweed on them. And that does not smell good, right? And on top of that, when you look at it, I mean, you can look at it and this is like a whole beach. It's not like a little log came up. It's like the whole thing is under 3 feet of seaweed or 2 feet of seaweed. And this is in the summer. And then you can look at it, and like if you look at a piece like this, you could probably find 25 pieces of plastic, right? And plastic bottles, there's toothbrushes, there's boat bumpers. I mean, it's just all sorts of stuff coming up. And you can't change that. There's nothing you can do to uninvent that other than stop so much junk. So
You might not be able to control the level of pollution, but the fact that it's capturing all that plastic could also be used to clean up the riverways.
yeah, but the seaweed, most of it ends up just sinking into the ocean. Some of it ends up on a beach. But that's a problem. People down there have suggested making it a biofuel, but then it has so much plastic and then oil and things like that. And he said, well, you really can't burn it. And then there are people that say, oh, I'll clean it up for you. But then you're not talking about a dump truck load. You're talking about a beach that's like 2 miles long, that is 3 feet of, this on it. And you start thinking of how much that is. And then you're talking about these Keys where an acre of land goes for $800,000. And they're not going to turn a key into a garbage dump with that going on. So it becomes a human problem, not just a scientific problem. So
Very depressing. What about the rest of you? Other questions?
Okay, so I have a question. When you're talking about the bryostatin and how y'all found a way to do it in like cheaper and stuff like that with
Yeah.
material. My question is your goal to like just say, hey, this is what we found, or do you think there could potentially be a way to where y'all get this out into the market, or no, considering that it already is?
well, so that's where you have to have a big brother that's on your side, right? And so my big brother is the National Institutes of Health, right? Because they're testing all our stuff. And so recently, so we've also done some bryostatins over here. That's like, we make that in the ocean. The other ones are copper complexes, but they're testing both of them now. And they recently asked me for, just out of the blue, some additional information about our compounds, right? And that was because we've done antibiotics, we've done the cancer drugs, and we've done the pox things with copper. And the same thing with the bio. They started asking, which is unusual, because usually when they test something for you, you sign an agreement that says it's all yours. We have no control over it, whatever. So they're starting to take an interest in some of it now. Because I didn't show the TV stuff, but we had molecules that no longer worked. That when we made a complex out of it, made them because of drug resistance, it worked again. And TB is another one. It's like smallpox. It's one of those great killers in the history of humanity. Right now on the planet, there's over 2 billion people that have TB, tuberculosis. The nation of India has 500 million of them. And there's a greater and greater concern there's no vaccine for it that works. There's a vaccine, but it doesn't work, BCG. And then there's a growing antibiotic resistance, right? And that's another thing that it's real easy to take TB. You can get it anywhere on the planet, just patients. and to make it drug resistance just by keep hitting it with small amounts of drugs until they become resistant, and to make it into a bioterrorism agent. So a lot of those things, it's not just like, oh, we have sick people. It's like this could devastate the plant type of thing. So much cheaper to do than having an aircraft carrier or a submarine or whatnot. So, but that's who are big, because corporations are very insulated. All right. They may have a couple of wings at some big schools that they interact with a lot. But typically it's for us that it's the government's the best way to go. That's how we're going moving along. So
Yes. Sure.
what
Go ahead. Okay.
he's looking angry back there, so we've got to call him. So
Why copper? I mean, it doesn't seem like it has anything to do with any of these things.
well, so let me tell you, copper is actually really interesting from a morbid point of view. We started with copper because cancer patients have higher than normal copper levels compared to healthy people. Right, and that's across all cancers. And it's there and then your body doesn't make copper, right? It's an element. So that means it's being retained and it's actually a nutrient. All right, so it's a nutrient for cancer. So there are people that do copper deprivation therapy where they try to move the copper out of you. And that will slow down the cancer, but it won't stop it, it won't kill it. So how I've done our cancer drugs, so there's something called the Warburg effect. And the Warburg effect was a Nobel Prize given for it like in 1933. But a cancer cell needs 15 times as much energy and building blocks as a healthy cell, right? And so that energy is most of the time in the form of sugars, but it also needs building blocks because cancer cells don't die, they just keep replicating, right? So healthy cells die and they get replaced, cancer cells just keep replicating. And so what we tried to do is hide our drugs inside either building blocks or nutrients to sneak them into the cancer as an uptake rate. And the analogy I use is like if you give a dog a pill, right? You give your dog a pill, a lot of times it'll just spit it out, right? Run away. But if you wrap it in bologna, Spot just takes it right down, doesn't even know how, and still wagging his tail. So that's what we wanted to do, was to use a trick to get the cancer drug. So if this cell is 15 times more likely than a healthy cell, then that gives it a specificity, right? So it's 15 times more likely to take up your drug with its nutrients than healthy. So that would lower the side effects. It would also make it more specific for this. So you could just lower the dose too. So we did that with sugars. We did that with fatty acids. And there was definitely a trend there where we saw it and it worked a little bit better, but when we went to copper, it worked a lot better. Right. And it was like, 200-fold better type things, 100-fold better types of things. So, and the second part of that is the copper deprivation. Well, just all the broths that we use for TB, for pox viruses, and for cancer cells, they never put copper in there, right? So it's not one of the nutrients. So most people just ignore that. They could care less. And you had to ask people, and you had to go check stuff to see if there was any copper in there. But they said no. Everyone said no, there's no copper in our broths. So what that means is that cancer cell or that TB bacteria have a deprivation of copper, right? Because low levels of copper are required for you, right? There's diseases that are named after not having enough copper. So you need low levels, but when you get high, that's when you have a problem. And so, but they were depriving them. And so what we think was they were depriving us of copper. So when we gave them our copper-based drugs, they took them up that much quicker, right? So there was even more specificity there than we realized. Whereas they are giving them sugars to grow, they're giving them amino acids to grow in those broths. And so that's when they took on a real interest, was when I started to point that out, because they never really thought about, is there copper, how much iron? It was just a broth that they bought and they mixed up, and that's what everybody used. So copper ends up being really interesting.
So copper it's not changing the drug. It's just kind of like a Trojan horse to
That's
carry the drug in.
that's the term we use in a lot of our papers, Trojan
Okay.
horse effect.
That's it.
And I didn't show it, but same thing. We had TB drugs. When you attach copper to it, there's one capreomycin, has terrible side effects. A lot of TB drugs. If you have TB and you go on a regimen, it lasts like 9 months, and every day you take 5, 6, 7 pills. And these aren't like little tiny pills. A lot of times these are these big horse pills, almost type thing. So a lot of people quit doing it, especially, and in a lot of countries, they make you come in to take them. So they watch you take them. I forget what they call it. They have a certain type of therapy name for it, but they don't just give you a prescription to go home and do it. Because a lot of people quit really quick. So they make you come into the doctor. If you don't show up, then they send a policeman to take you into the doctor. So, well, because then you can start spreading it to everybody. So one sneeze of a TB patient can affect up to 40 people, right? So imagine being on a subway in, New York, and someone's like, achoo, achoo, and it goes 80 people with, TB. So,
Or on one of those trains in India.
yeah, you've seen those things. I mean, they sit on the top of the roofs. They're so
Right.
crowded. So that's why a hot and crowded city is just a great place for, for those diseases to spread and for bioterrorism to start. So,
Good question. This is more a question about your teaching. It seems like some of what you're explaining to us in these examples is kind of a combination, results from a combination of deep knowledge, but also some serendipity and discovery. And how do you encourage that sense of discovery in your students?
well, we do projects, right? And what I don't do is expect them to do the same thing I do, right? Because I've been doing it for a long time and I'm kind of independent. And so you take them through the process of doing it, right? And I think that's important, right? So you give them like deadlines this week, this week, this week, you show them what to do. So you kind of take people through the process of doing it. So are there any, who in here is doing a poster with me? So the ones that are doing it from the freshman class, right? So they're doing a Sudoku puzzle, right? So everyone knows what Sudoku is, but we turned it into a learning tool, right? And so what they do is, Pierce, why don't you tell us about your Sudoku? What's it on?
I'm doing mine on like plants in the southeastern United States. So he basically told us we have to make one big topic and then 9 subtopics as like Sudoku is 1 through 9. And then we have to choose 9 like subtopics of each of them. And we just make a puzzle like that. So like one of my main subtopics will be trees, and then I would have 9 different types of trees, and then like bushes, and then 9 different types of bushes. And we have to make a puzzle into it. So it kind of makes it like a fun way to learn about whatever our topic is.
So instead of having like 1 through 9 on a Sudoku, he has the abbreviations of the things. So going in, someone that's going to play his puzzle knows nothing about so he might have so let's say like flowering plants, I don't know, and then he'll have 9 different types, right? And have the names written there with the abbreviation. So if you go in and play that, you're now learning about 81 different types of plants, right? And they each have a little phrase next to them, like a key thing, like attracts bees, chases away lawyers, who knows what, And so there's a little fact about it, a little fun. That's a Snapple thing. Like Snapple sells $6 billion a year in drinks, and everyone has seen how many kind of drinks come and go, and they're still around. A lot of people, the business people, call that the Snapple effect. All right, so there's things like that where if someone's going to do his Sudoku, who else did a Sudoku? So, Kayla, why don't you tell us about yours?
For me and Rio, we're doing forensic science. And like he said, we have the 9 different subtopics, and I'm a biology major, but Rio's
I'm actually going to forensics.
yeah. So it was really interesting to kind of learn about the different things that go on within forensic science. But I think my favorite part was actually working through the Sudoku puzzles, because we have to solve them before we put it on the board.
Yep.
So it was really like nice I've only played Sudoku once, so it was actually really fun to actually like sit there and have to solve and figure out how the numbers go in there and set it up.
There's also did we do 5 different levels, 5 different difficulties, using different style types. So one of them was the jigsaw style type that we used for, I think, our medium or harder one of the 2. But there was also, we did the masterclass Sudoku puzzle as one of the killer ones. And the killer Sudoku puzzles, if you didn't know, they have little sections that you have to equal to a certain number. So they have a really specific place. You can't just randomly put letters and numbers down. It's very intentional on how to solve this.
So we learned a lot.
So I gave them an outline, and then I said, go,
Yeah.
and so they work as groups and they do it. They like doing, with social, they usually like doing a little bit more than by themselves. And then they'll give presentations at the conference, and now there's peer pressure involved. So they may not care what I think, but when your friends go around and look at their posters, there'll be a lot more peer pressure on them. So you guys didn't know that, did you? There's a whole strategy there. So
I've seen all the titles, and I'm really looking forward to to seeing them.
Carlton Kenya are giving a poster also. Once you guys, and that was a project we did in class. Once you guys summarize it.
Okay, so with me and my partner Ariana, which is not here today, but we're doing penicillin G, and basically we're just we run them through something called sparring, and we just take the NMR spectra of that, and we're just getting the compound penicillin G, and we're spacing arrows from those peaks that we were able to see. And that's basic.
So it's a complex analytical technique,
Yeah,
right? And so it takes a while to figure, it's like a really hard Sudoku. It takes a while to figure it out. And so with their project, they have to do all this simulations, right? Because a lot of times it's hard to get NMR time on big instruments like that. So they get a real good feel for what the spectra are, how does that relate to, and we use penicillin because everybody's heard of it, right? It's an interesting, if I took some obscure drug, there'd be less, the interest level would go down a little bit. So it's things like that, bring them in a little bit. So it's kind of like making a hard topic into something that's a little more enjoyable, a little more social. I try to have everything be social. That seems to help you rather than just sitting in a room by yourself. And people usually end up, and they're doing like the NMR one is the whole class. There's 9 students in that class. And so they work as a team, right? So there's a lot of teamwork involved in that too. So.
it's wonderful. So it builds a lot of skills.
Yep.
Yeah, I like it. It's impressive work. I would think that this style, I'm surprised that, always have been, that our science department or college doesn't get more press than it does, because the things that students do here are far superior to what's coming out of like UGA. And that mainly because the students get the hands-on treatment, they get to go out with a publication, something like that. And I don't know how you feel about the competition to get the students.
Well, I have 12 students this semester that are in a research class with me, and I had to say no to probably about 12 others type of thing. And even 12 is probably too much, something, because, but that said, they want to do that. So I pick topics that they find interesting, right? So with diseases, I call it the Walking Dead effect. Everyone's seen that show. My wife's obsessed with that, and I joke with her. I said, well, what's going to happen in this minute? Somebody's going to get stabbed, and so it's just kind of like nonstop war. So when you do stuff like with diseases that people understand, right, they can understand TB or pox or cancer, then it's the motivation level and the interest level goes up a lot. When I first came here, I was doing high temperature plasma physics, right? No interest whatsoever, right? So and I'm like, oh, it's the solar flare in a container, blah, blah, blah. And just no interest. As soon as I started moving over to the quinine type stuff and the outdoors type stuff, then that's when the interest just really, really went up. So,
Well, yeah, you get to camp in the Keys, so yeah.
well, yeah, if you camp with us in the Keys in the summer, you may not, it's not as pleasant and as romantic as you think with the oceans and the heat. So,
Yeah, that's true. But it's been over the years, watching the students go through. That's one of the things that I really enjoyed, is watching and seeing the students who get their names on not only publications, but some of the grant things and the NIH stuff. That's huge.
yeah. Well, it's a good resume. It's resume material. And so like the pre-med students, hey, sometimes I tell them, I said, you're going to go in for an interview and there's going to be a bunch of 45 and 50-year-old adults there. They're not going to be impressed if you told them you were in a fraternity and you were picking up garbage on the side of the road. I said, but if you tell them that you published a paper on a new antibiotic and then you can talk to them about it for 20 minutes, they're going to be impressed. So I said, there's those key moments in your life. And that's a key moment if you really want to do like med school or a good grad school or, going to the military or something. So that one discussion can play a pretty big role in how things turn out. So.
Yeah, wonderful. I know that people have to get to their 1 o'clock classes, even though the clock says it's 12. But I do appreciate you being here. I appreciate all of you coming. This is it is recorded, so I will get it up on the website for anybody who wants it. And now you know where you go to play games, chemistry.
Chemistry.
So thank you.
All right. Well, thank you for having me. Thank you for having me.
Oh, anytime, anytime.
Guess I want to do one thing.
Oh,
I was talk too fast, don't I? I have that New York
No, I don't.
movie still.
I don't think so. Okay, how am I gonna turn this off?
I was going to do it.
It's down here.
Really.
Oh.
Really, really well. Thank you for coming. Yeah. I love it. So is also what's the money gonna start going to chemistry now?
Well, it's just fun to see how it lights them up and gets them really, really excited.
but it's not 11.
They dive into the project.
Well, that's what with the